Come to order. Without objection, the chairman is authorized to declare recess at any time. Before I deliver my opening remarks, I wanted to note that today the committee is meeting both in person and virtually. I want to announce a couple reminders to the members about the conduct of this hearing. First, members and staff who are attending in person and are unvaccinated against COVID-19 must stay masked throughout the hearing. Unvaccinated members may remove their masks only during their questioning under the 5-minute rule. Members who are attending virtually should keep their video feed on as long as they are present in the hearing, and members are responsible for their own microphones. Please also keep your microphones muted unless you are speaking. Finally, if members have any documents they wish to submit for the record, please email them to the committee clerk, whose email address was circulated prior to the hearing. I'd like to thank all the witnesses for joining us today to discuss the future of the bioenergy research enterprise. As some of you know, I spent 20 years in the energy industry before I came to Congress, but I'm sure all of you have read that 1998 New York Times bestseller, Advanced Processes for Ethanol and Electricity Co-Production from Lignocellulosic Biomass. As I don't need to tell you, that was, of course, the title of my master's thesis, which caused me to spend 3 years building, operating, and modeling biofuel fermentation and energy recovery systems. And I think it's for the good of our planet and for my sanity that the technology has come a long way since then. In fact, in December of last year, I was on the first passenger flight powered by 100% sustainable aviation fuel, flying from the greatest city of Chicago to Washington, D.C. Although that was a historic moment, we still have some significant barriers to overcome. Cost, of course, remains high, with sustainable aviation fuels costing about 4 times as much as traditional jet fuel. But in addition to that, we simply don't have enough supply. 95 billion gallons of jet fuel was consumed in 2019, and that same year, less than 2 million gallons of sustainable aviation fuels was produced. I'm encouraged by President Biden's Sustainable Aviation Grand Challenge that aims to reduce the cost, enhance the sustainability, and expand production of these fuels, which I understand LanzaTech is taking part in by pledging production of 1 billion gallons of these fuels per year by 2030. So I'm really looking forward to Dr. Harman's testimony, and not just because LanzaTech is headquartered in my backyard. I also really look forward to learning about the status of the technologies to create these fuels and where there are constraints and opportunities in the upstream feedstock supply. I'm also pleased that the Department of Energy sees this urgent need and is focusing its bioenergy research on the fuels of tomorrow. Sustainable, cost-effective feedstocks that can scale down and move refinement closer to the feedstock sources would enable a distributive model that revives local economies. As an example, the Center for Advanced Bioenergy and Bioproducts Innovation, which also happens to be located in Illinois, works to create ecologically and economically sustainable feedstocks by using a plants as factories approach that prioritizes efficient land use, soil health, water health, clean air, and of course, emissions reductions. As we saw in the recent IPCC report, the science is overwhelmingly clear that we have to get to zero greenhouse gas emissions as quickly as possible. Sadly, as we all know in this committee too well, what is scientifically necessary vastly exceeds what is politically on the table at the moment, and that's why I'm so proud to be on the Science Committee where we get stuff done. I hope that in convening this hearing, we can ensure that our R&D dollars are spent wisely and that we prioritize some of the less sexy, hard to decarbonize industries. Now more than ever, we have to figure out how to decarbonize these hard-to-abate sectors: cement, steel, aviation, and shipping. These are sectors that use carbon and fossil fuels often not as an energy source, but as a chemical reducing agent, and or they depend on liquid fuels that have the kind of mass and energy density that's very difficult to replace with other sustainable fuel stocks. Bioenergy is the unique renewable fuel source that can serve both of those needs, and I'm excited to hear from our witnesses where we can best target our research and development in this space. The IPCC report also concluded that bioenergy has significant potential to mitigate greenhouse gases if resources are sustainably developed and efficient technologies are thoughtfully applied. If we do this right, we can pinpoint how biofuels and bio-based chemicals can be utilized where they would be most effective in enabling a transition to a 100% clean economy. Finally, I don't think we can emphasize enough the impacts that most Americans, and indeed all of the world right now, is experiencing due to our over-reliance on a globally traded, geographically limited, environmentally detrimental, and ultimately finite commodity under the control of some genuinely crazy people. This is not a problem that we can drill our way out of. No amount of oil that we extract from within our shores can make a meaningful dent in the massive price spikes that always follow the kinds of geopolitical volatility that people like Mr. Putin have created. We absolutely must pursue ways to produce more sustainable and domestically grown solutions to meet our energy needs. By doubling down on our innovation enterprise, we can electrify the bulk of many sectors and create sustainable fuels to power those otherwise hard-to-abate sectors. Knowing what we know today, we just can't keep doing more of the same and expecting a different outcome. I want to again thank our excellent panel of witnesses assembled today, and I look forward to hearing your testimony. With that, I yield back, and the chair now recognizes Mr. Weber for an opening statement.
Thank you, Mr. Caston, for filling in for Chairman Bowman and for running what is our first hybrid hearing in about a year, I think. I'm glad, like you, I'm glad to see some faces here in person, although it's hard to recognize y'all without your masks. Today, we will examine a promising clean energy technology area that should play a role in all of our all of the above energy strategy. Bioenergy is a broad term that refers to the use of biomass and waste resources to produce energy and related products like biofuels and biogas. The applications of bioenergy seem almost endless, from sustainable aviation fuel that you talked about, to recycling and waste-to-energy technologies. Bioenergy has the potential to benefit not just the U.S. energy sector, but a variety of industries, including manufacturing and agriculture. The Department of Energy has led the way in driving U.S. innovation in bioenergy technologies, but like most technologies we talk about here at the Science Committee, there is still work to be done and progress to be made. While some biofuels, like ethanol, are mature energy sources, we have just scratched the surface of what is possible when it comes to new, more efficient, advanced biofuels and bioproducts. That is what today's hearing is about, the next generation of bioenergy R&D. Along with Chairwoman Johnson, Ranking Member Lucas, and Chairman Bowman, I was proud to lead the DOE Science for the Future Act and see it pass on an overwhelmingly bipartisan vote on the House floor last summer. This bill contained a comprehensive reauthorization of DOE's Biological and Environmental Research Program, which conducts early-stage research to advance our ability to use biological systems for energy technology. This reauthorization is absolutely necessary for the success and commercialization of next-generation bioenergy technologies. Without support and updates to BER's basic research mission and facilities, like the bioenergy research centers, we could be stuck with the same conventional biofuels and bioproducts that may never be cost-effective, much less widely adopted. The updated language in our bill provides guidance to DOE's activities and modernizes their research focus to align with current capabilities, needs, and demands. DOE also conducts bioenergy research, development, and demonstration activities through its Bioenergy Technology office, which is housed with the Energy Efficiency and Renewable Energy, EERE office. While this office is focused more on mature technologies and their commercialization, it plays a valuable role in the full research and development cycle. BER and the Office of Science target the most fundamental industry-shifting breakthroughs with basic research, but BEDO and EAR then help to take those breakthroughs and apply them to a technology suitable for widespread deployment. But as my colleagues have heard me say often, applied energy research on the government's dime has its limits. That's my 10 cents worth at least. There are times when help for demonstration and commercial application makes sense, but the federal government has no business picking the winners and losers of the energy market. Therefore, there comes a time when every technology, bioenergy included, pardon me, should be taken off government support and allowed to either flourish or flounder in the free market. So while I support much of the work BEDO and EAR, I don't want my words to be misconstrued as an open invitation to expand these programs irresponsibly. I believe we should start with robust funding and support for the Office of Science and then allowed EERE to capitalize on their most promising breakthroughs in partnership with the private sector. I look forward to today's hearing too, Mr. Chairman, and learning how this basic research to commercialization cycle for bioenergy can be streamlined and improved. We have a diverse panel here with witnesses from National Lab, a DOE Bioenergy Research Center, academia, as well as the private sector. Between all of those witnesses, I'm sure we'll hear about a bright future with bioenergy. So I want to thank each of them for testifying today. And with that, Mr. Chairman, I yield back the balance of my time.
I believe our chairwoman is not present, so the chair will now recognize the ranking member of the full committee, Mr. Lucas, for his opening statement.
Thank you, Mr. Caston. And I'd like to express my appreciation to Chairwoman Johnson and the entire majority staff for their work to hold this hearing in hybrid format. This is an exciting step towards transitioning back to in-person hearings, and I look forward to seeing the rest of my colleagues and future witnesses in our hearing room sometime soon. Even before serving as ranking member of the Science Committee, I've been an advocate for an all-of-the-above approach to our energy security. Bioenergy, which is one component of that mix, carries tremendous potential as an energy resource for our country, especially given our nation's strong agricultural capacity. However, additional research and development, particularly fundamental research and cross-sector collaboration, is needed to unlock its full potential. But that must be done in a responsible, targeted manner. To that end, I was proud to help lead the Science Committee's bipartisan efforts to support the Department of Energy's Office of Sciences, Biological and Environmental Research, or BER program, by passing the DOE Science for the Future Act in the House last year. Among many things, this legislation modernizes the BER program and provides additional guidance for our bioenergy research centers. It helps them address cutting-edge challenges for the expansion of the biofuel and bio-based materials industry. We still don't have certainty on the path ahead for the DOE Science for the Future Act. It's been 4 months since Leader Schumer and Speaker Pelosi announced that we would go to a conference on a competitiveness legislation, and we're still waiting. The BER program is just one among many strategic and bipartisan initiatives that we in this committee room worked on carefully together. I'd like to move it forward soon. So I look forward to working with my colleagues on both sides of the aisle and in both chambers to find a way to get this legislation across the finish line. I want to thank our witnesses for sharing their expertise and discussing strategies to address the most critical bioenergy R&D needs. Thank you, Mr. Caston. I yield back the balance of my time.
If there are members who wish to submit additional opening statements, your statements will be added to the record at this point. This time, I would like to introduce our witnesses. Dr. Jonathan Mayo is the Chief Scientist in the Energy Processes and Materials Division at Pacific Northwest National Laboratory, or PNNL. He's also an adjunct faculty member in the Biological Systems Engineering Department of Washington State University, or WSU, and the co-director of the WSU PNNL Bioproducts Institute. Previously, Dr. Mayo served as the Director of Bioenergy Technologies Office at the Department of Energy for over 6 years. Dr. Andrew Leaky is the Director of the Center for Advanced Bioenergy and Bioproducts Innovation and the head of the Department of Plant Biology at the University of Illinois, Urbana-Champaign. He joined the university as a Fulbright Scholar in 2002. He's received the Calvin Benson Prize for Excellence in Early Career Research and has been elected as a Fellow of the American Association for the Advancement of Science. Dr. Laurel Harman is the Vice President of Government Affairs at LanzaTech. She has over 30 years of experience in policy and technology development. In her current role, Dr. Harman provides policy direction on legislative and regulatory matters and develops public-private partnerships to support research and demonstration projects. She also serves on the board of LanzaJet and is the Vice Chair of the Board of the Roundtable on Sustainable Biomaterials. The Chair now recognizes Mr. Meyer for the introduction of our final witness.
Thank you, Mr. Caston, and it's my pleasure to introduce a fellow Michigander, Dr. Eric Hegg, the Associate Dean for Budget, Planning, Research, and Administration in the College of Natural Science at Michigan State University. Although not located directly in my district, Michigan State's research, students, and faculty all have a tremendous impact across the state. When it comes to the Science Committee and national research priorities, it's always great to have Michigan and its unique skills and needs represented. Dr. Hegg is an expert in biochemistry and molecular biology. Specifically, his research looks at how structural components of the plant cell wall can be used to form biofuels and bioproducts. And relevant to today's hearing, Dr. Hegg has served in a variety of roles within the Great Lakes Bioenergy Research Center since it was first established in 2007. Most recently, he served as the MSU subcontract lead for the GLBRC before transitioning to his current role as Associate Dean. Dr. Hegg has been a Big Ten Academic Alliance Leadership Program Fellow and an Academic Advancement Network Leadership Fellow. And in 2019, he was elected a Fellow in the American Association for the Advancement of Science. His knowledge in the field of bioenergy and history with DOE's bioenergy research centers are invaluable to today's discussion, and I look forward to hearing more in his testimony. Thank you, Dr. Hegg, for being with us today, for being a voice for all of Michigan, and I yield back the balance of my time.
Thank you all for joining us today. As our witnesses are no doubt aware, you will each have 5 minutes for your spoken testimony. Your written testimony will be included in the record for the hearing. When you've all completed your spoken testimony, we will begin with questions. Each member will have 5 minutes to question the panel. We will start with Dr. Mayo. Dr. Mayo, please begin.
Thank you. Good morning, and thank you, Chairman Caston, Ranking Member Weber, and Full Committee Ranking Member Lucas, and members of the subcommittee for the opportunity to participate in this important hearing on bioenergy research and developing the fuels and chemicals of tomorrow. As you've heard, my name is Jonathan Mayo. I am a chief scientist for the energy process and materials at the Pacific Northwest National Lab. That's in Richland, Washington. I'm also an adjunct professor at Washington State University and serve as the co-director of the PNNL WSU Bioproducts Institute, which advances science to reduce environmental impacts of fuels and products. Previously, I served as the director of the Bioenergy Technologies Office in the Office of Energy Efficiency and Renewable Energy. In my testimony today, I will focus on 3 main points about the state of bioenergy research and development and its importance to our cleaner energy future. First, we must expand our understanding of real-life biomass feedstocks. Second, we have a great opportunity to turn today's waste carbon streams into tomorrow's carbon resources. And third, bioenergy and bioproducts will be most important for reducing emissions in segments of our economy that are difficult to electrify, such as aviation, marine, and industry. Decades of investment in fundamental chemistry, biology, catalysis, computational modeling, and other science disciplines have positioned us to convert biomass and waste to useful fuels and products. Much of this work has depended on DOE's world-class scientific user facilities like the Environmental Molecular Sciences Laboratory at PNNL and the Joint Genome Institute at Lawrence Berkeley National Lab. To take the insights of fundamental science to scale and realize commercial impact, we must look to real biomass with all its variability and imperfections. Producing bioenergy and bioproducts at scales required to meet carbon reduction goals, bioenergy technologies must work not only for the optimal feedstocks we use in the laboratory, but must be robust against variations during industrial processing. Consider corn stover as an example feedstock. Real bales of corn stover sit out in the elements and will contain everything from soil to twine to farming tools. Bioenergy and bioproduct facilities must have resilient processes to still efficiently produce fuels and products. In demonstration and commercial scale facilities, feedstock variability has led to undesirable outcomes. DOE created the Feedstock Conversion Interface Consortium, or FCIC, to begin to scientifically understand and address critical feedstock variability issues. FCIC researchers across 9 DOE national labs provided critical insights on potential methods for detailed characterization of feedstock variability and understanding key properties of feedstocks that impact facilities' performances. To the second point, we can turn today's wastes into tomorrow's carbon resources if we invest in the RD&D to characterize wastes and further develop conversion processes. DOE researchers estimate there is a potential for 1 billion dry tons of biomass to be converted to approximately 62 billion gallons of fuel annually, enough to supply all of aviation, marine, rail, and a significant portion of the heavy-duty trucking. However, these analyses have assumed approximately 23% of those billion dry tons would be derived from woody and herbaceous energy crops, which have been slow to scale up. If we expand our view of renewable carbon feedstocks, we find significant additional carbon in our waste streams, from municipal solid waste to food wastes and waste gases, to name just three. By developing science and technology to utilize these wastes, we can increase feedstock supplies, reduce landfill volumes, disposal costs, and reduce land use impacts. One exciting potential conversion process for waste streams is hydrothermal liquefaction. It combines heat and pressure to create a biocrude. A recent analysis by PNNL and National Renewable Energy Lab showed that wet waste have potential to produce 4.5 billion gallons per year of renewable diesel. Finally, bioenergy and bioproducts have the biggest potential to impact hard to electrify segments of our economy, such as aviation, marine, and industry. The aviation segment remains far from viable for electrification of wide-body jets due to fuel energy density demands. There are commercially viable technologies today for converting fats, oils, and greases to sustainable aviation fuels, or SAFs. About 3 million gallons was made in 2019. However, the US aviation sector used 26 billion gallons of jet fuel in the same year. There are not enough fogs available as feedstocks to meet that need. Recent research has started to use waste such as carbon monoxide, hydrogen, and carbon dioxide that LanzaTech will talk about. In the collaboration with PNNL, have developed technologies to efficiently ferment this mixture to alcohols, which can then be taken to SAFs. The technology will help meet the DOE, DOT, and USDA Sustainable Aviation Fuel Grand Challenge of producing 3 billion gallons in the US by 2030. In conclusion, by looking at an array of biomass and waste feedstocks, better characterizing their real-world properties, we increase potential to bring bioenergy and bioproducts to bear. We can reduce the carbon intensity of critical but hard to electrify segments of the economy and meet our goals for dramatic global emissions. Thank you for your time today, and I look forward to your questions.
Thank you, Dr. Mayo. Next, we will have Dr. Leakey.
Acting Chairman Caston, Ranking Member Weber, and other distinguished members of the subcommittee, thank you for the opportunity to participate today. I'm a professor and head of the Department of Plant Biology at the University of Illinois, Urbana-Champaign. Originally from Great Britain, I came to the United States in 2002 as a Fulbright scholar. Since 2020, I have directed the Center for Advanced Bioenergy and Bioproducts Innovation, or CABI, which is the newest of 4 bioenergy research centers, or BRCs, that the Department of Energy is funding. CABI is comprised of over 300 scientists from 23 institutions in 17 states. Today, I was asked to discuss bioenergy and bioproducts research. Based on my personal experience, I aim to convey to you the need for next generation renewable bioenergy and bioproducts, the scientific goals and progress of the BRCs, and the opportunities to train a diverse workforce that can positively impact every corner of the country. I represent myself at today's hearing, and the views I express are my own. The transportation fuels and petrochemical sector is a global multi-trillion-dollar per year industry. There's enormous potential to produce abundant renewable bioenergy and bioproducts from plant biomass. This would, 1, reduce reliance on foreign sources of energy and improve resiliency to international conflicts or natural disasters. 2, support farming communities in developing a more sustainable and resilient agricultural system. 3, develop a more just economy in which additional individuals and communities receive economic benefit from the production of fuels and chemicals, including in rural areas. And 4, to reduce the greenhouse gas emissions from fossil fuel that are driving climate change. Liquid biofuels have special potential to replace fossil fuels for modes of transportation where batteries are too heavy to store sufficient power, and where charging infrastructure is not easily connected to sources of clean electricity. Sustainable biofuels for aviation, marine freight, and heavy-duty long-distance trucking are notable examples. Decarbonizing the transportation sector of the economy is important because it currently accounts for the largest fraction of US CO2 emissions. However, further research and innovation is needed for biofuels and bioproducts to meet their full potential. The BRCs aim to provide the scientific discoveries and technologies needed to develop economically and ecologically sustainable domestic biofuels and bioproducts. This requires improved cropping systems that produce more and greater value biomass per acre while achieving sustainable greenhouse gas balances. It also includes more efficient technologies to deconstruct biomass and convert it into valuable fuels and chemicals that decarbonize our energy systems and products. In my written testimony, I detail scientific discoveries and cutting-edge tools made by CABI. A few highlights from the last 4 years include engineering bioenergy grasses to produce substantial amounts of oil, which can be processed into a drop-in biofuel, engineering microbes to greatly enhance conversion of plant-derived sugars into a platform chemical that can be used to make decarbonized detergents and lubricants, leveraging satellite imaging and computer simulation models to identify land that is best suited to produce bioenergy crops, accelerating research and innovation through advances in robotics and artificial intelligence, as well as the sequencing and editing of plant and microbial genomes, and development of software for conducting techno-economic analysis and life cycle assessment. More broadly, since 2007, thousands of BRC researchers have made discoveries leading to more than 4,000 scientific publications, 670 patent applications, 280 of which have been licensed, and 15 startup companies. A focus on technology transfer and commercialization is a notable feature of BRCs. CABI currently has partnerships with 11 companies, allowing us to learn the challenges faced by industry and provide solutions to them. BRC work of this type is greatly aided by sustained funding for research that spans the entire value chain, thereby forming the basis for the US bioeconomy of the future. Additional benefits come from collaboration among the BRCs and DOE's national labs, Joint Genome Institute, and Environmental Molecular Science Laboratory. Along with the other BRCs, CABI is committed to training a diverse bioenergy workforce. Our scientists contribute to this effort through many outreach and educational activities. I'm especially excited about our new internship program for undergraduate students from traditionally underrepresented groups. In conclusion, I came to America because I believed it created the greatest opportunity for scientists to help tackle clean energy, climate change, and sustainable agriculture. 20 years later, my experiences working at a top land-grant university have greatly bolstered that belief. We all have reason to be proud of this country's bioenergy research enterprise and to be optimistic about what it can do to deliver many benefits for our society. Thank you, and I look forward to addressing your questions.
Thank you, Dr. Leaky. Dr. Harman, you are now recognized for 5 minutes.
Thank you, Acting Chairman, Mr. Caston, Ranking Member, Mr. Weber, and members of the subcommittee. I really appreciate this opportunity to share LanzaTech's experience and our perspective here today. LanzaTech is a carbon capture and transformation company headquartered in Illinois with offices around the world. Our goal is to replace virgin fossil carbon with carbon from waste, creating what we call a circular carbon economy. Because even in a decarbonized world, most of the products in our daily lives, from clothes to jet fuel, need carbon. Our technology uses a biocatalyst, a bacteria or microbe, like beer making, except we use bacteria and waste carbon instead of yeast and sugar. With this biocatalyst, we can turn all kinds of carbon-rich waste streams into products, from the industrial emissions you heard earlier, like steel mill off-gas, to solid waste, including biomass residues and municipal waste. This technology is operating commercially in 2 plants today, producing ethanol from industrial emissions. And several other plants are in design and construction around the world. We've created custom microbes using technologies, as you just heard described, which are capable of producing over 100 different molecules. Taking a step back, to advance bioenergy, we need a robust bioeconomy, which includes biological processes like ours, the use of bio-based feedstocks, and hybrid pathways, such as Dr. Mayo described, that combine biochemistry and thermochemistry to maximize carbon efficiency. The bioeconomy can free us from virgin fossil carbon and also from the massive centralized refinery model on which we rely today. Production facilities that are matched to the scale of waste feedstocks can be located throughout the country. This means they can be located in heavy manufacturing centers. They can be located in rural communities or in urban centers. These improve the local environment as well as creating high quality jobs. LanzaTech has partnered with the Department of Energy in projects from basic research, from BER, for example, through process optimization and scale up in BETO and the Advanced Manufacturing Office. I provided many examples in my written testimony, but here I want to highlight DOE's role in developing collaborations. You've heard that touched on already. DOE has allowed LanzaTech to collaborate with world-class universities and with the national labs. And these collaborations are developing new basic insights. They're developing new computational and experimental tools that accelerate discovery. They're expanding feedstocks to new materials like waste CO2 or waste plastics. They're also intensifying the conversion processes themselves to increase energy and carbon efficiency, and scaling them up to enable commercial implementation. One example is the alcohol to jet, or ATJ technology that Dr. Mayo referenced, developed initially at PNNL, converts ethanol into sustainable aviation fuel and renewable diesel. After initial proof of concept, VITO funded a project for a pathway to show that sustainable aviation fuel could be produced from biomass using our gas fermentation and the ATJ process. VITO also supported PNNL to produce fundamental data that catalyzed additional investments by LanzaTech and industry partners to scale up the process and produce thousands of gallons of fuel. Some of that fuel, made using ethanol that came directly from steel mill emissions, was used in a transatlantic commercial passenger flight with Virgin Atlantic, a 747 flying across the ocean on steel mill emissions, a great demonstration of the circular carbon economy. The DOE partnership continues in a project to support a 10 million gallon per year facility in Georgia. And in 2020, we formed a spin-out company, LanzaJet, to commercialize this technology with support from Mitsui, Shell, LanzaTech, Suncor, and British Airways. This is a great example of DOE engagement throughout all stages of technology development and deployment. In closing, I'd like to emphasize three main points. DOE's RD&D programs must be technology and feedstock agnostic to advance all technically, economically, and sustainably viable pathways. DOE funding is, as I've emphasized before, needed not just for R&D, but also for demonstration and deployment to ensure plants get built and are built where they are needed. And the expansion, the bioenergy concept needs to be expanded to chemicals and materials that require carbon and are made from petroleum today. Finally, I would like to emphasize that the DOE needs support also for the staff and the systems that it will enable the department to accelerate the selection and execution of these projects. Thank you again. I look forward to responding to the members' questions.
Thank you, Dr. Harman. And finally, we have Dr. Hegg. You are recognized for 5 minutes.
Acting Chairman Caston and Ranking Member Weber, thank you. Thanks also to Representative Meyer for your introduction, and to Representative Stevens for giving me my first opportunity to testify back in 2019. It is my honor to be here today. I am representing myself, and the views I express are my own. I am a professor at Michigan State University and Associate Dean for Research in the College of Natural Science. Previously, I was the MSU subcontract lead for the Great Lakes Bioenergy Research Center. In all of these roles, I have experienced the critical partnerships that exist between the federal government and universities. Several federal agencies have funded my research, including NIH, NSF, USDA, and 3 different agencies within the DOE, BES, BER, and VITO. My research focuses primarily on bioenergy and environmental research, and I'm an inventor of bioenergy and bioproducts technology. It is within this context that I provide today's testimony. Federal support for interdisciplinary centers is critical to addressing society's grand challenges. Centers bring together researchers from disparate fields, stimulate innovation, and tackle complex problems in ways not possible with smaller projects. For bioenergy, this includes bringing together scientists from agronomy, genetics, and plant biochemistry to develop dedicated bioenergy crops, biogeochemistry and microbial ecology to understand nutrient flow, and microbiology, chemistry, and engineering to convert the biomass into biofuels and bioproducts. Overarching is the work of computational scientists who ensure that the strategies identified are economically and environmentally sustainable. Without large centers, new technologies developed in one area might not integrate across the entire pipeline. Centers are therefore essential to identifying sustainable and holistic solutions. At the same time, however, it is critical to maintain and even increase funding for creative individual research projects, hallmarks of U.S. innovation. Smaller projects often adapt more quickly to unexpected results, thereby opening new avenues of inquiry. These individual breakthroughs can themselves become the basis for integrative research. Single investigator projects are therefore vital to the success of large centers, as well as to the entire scientific enterprise. Examples relevant to bioenergy are found across the entire pipeline. In addition, discoveries made in one field can unexpectedly benefit other research areas, often years later. It is therefore nearly impossible to overestimate or predict the full impact of basic research. Once promising technologies are shown to be compatible in an integrated system, they must then be scaled. Technologies established at the bench, however, often encounter unanticipated challenges as they move to the industrial scale. Demonstrating they can be overcome is key to obtaining industrial investment. BETO has been important to my own research, enabling us to optimize our technology and begin the scaling process. The work has led to a new patent and an additional patent application and a potential industrial partner. To take full advantage of federal investments in basic research, BETO and similar programs should be continued. Critical to the bioenergy research process is developing the workforce needed for scientific breakthroughs to maintain U.S. leadership. Large integrated centers are ideal environments for educational development. They provide cutting-edge research experiences while exposing students to multidisciplinary teams vital to industrial research. Authentic laboratory experiences also reinforce concepts learned in the classroom, teach critical thinking, and encourage creativity. Because many undergraduates must work to afford tuition, paid research programs improve diversity, equity, and inclusion, thereby significantly impacting the quality, quantity, and diversity of the future workforce. Opportunities such as NSF's RAU program and the DOE's internship program are hugely successful. Competition for these and related programs is often intense, and additional funding to expand them would have a significant impact on the future workforce pipeline. In the coming decades, there are opportunities for growth that will increase the impact of federal investment in bioenergy research, ranging from expanding long-term studies to increasing coordination among the agencies under the purview of this committee, including the DOE and NSF. This coordination would be especially powerful if expanded to include other agencies supporting bioenergy research, including the USDA. These proposed steps would ensure highly integrative and synergistic research that avoids duplication and promotes coordination in tackling society's complex grand challenges. Thank you for inviting me to testify and address any questions that you may have.
Thank you to all of our witnesses. At this point, we will begin our first round of questions, and I will recognize myself for 5 minutes. Dr. Harman, the recent report entitled Sustainable Aviation Fuel Review of Technical Pathways, funded by the Department of Energy, finds that the United States refinery production of renewable diesel exceeds 300 million gallons, but only 2 million gallons of sustainable aviation fuels made with the same technology were produced. The report does say that there's some of that is a difference in production cost, but it says that the difference in renewable diesel production and sustainable aviation fuels is primarily driven by policy. Can you give us a little understanding of what those policies are and what policies we would need to get greater sustainable aviation fuel production?
Thank you for that important question. The first priority, I think, is to recognize that road transport has benefited from a long history of incentives to which sustainable aviation, or SAF, has not really been privy. Even when the California Low Carbon Fuel Standard was developed, aviation fuel was not a compliance mechanism. And what that meant is that even though most technologies to produce SAF also produce diesel, industry focused on production of diesel, and much of that was provided to the California market. When the LCFS was opened up to SAF, then SAF production increased, and then including the attraction of imports. What I would also like to add is that what we do not have today are policies that selectively promote aviation fuel. And an example which is on the table would be the SAF blenders tax credit. And that's something that I'd be happy to follow up, or my colleagues would be happy to follow up with the committee on. Finally, I would note that there are fuel policies which don't selectively discriminate against SAF, but the RFS, for example, is quite limited in the pathways that are acceptable. And so many waste feedstocks are actually not acceptable under the RFS, and that expanding the RFS to include waste such as industrial emissions, waste CO2 would also have the benefit of accelerating production of SAF.
So I'd love to follow up on that feedstock question. We've got this 95 billion gallons a year of jet fuel production and 2 million with an M gallons of SAF. With current production technologies that you have, how much could you ramp up before you would be completely maxed out on current feedstocks? And what technologies would you need to develop, or they already exist? I know Dr. Mayo had talked about carbon monoxide, but I'm assuming that's produced from something else upstream. What does the technology look like, and what does the feedstock look like in a feedstock unconstrained world?
All right, so I'll speak to alcohol to jet, because the intermediate used by alcohol to jet is ethanol. Ethanol could be produced using many different technologies from a huge array of feedstocks. Very specifically, for example, using our technology, we can take carbon monoxide rich steel mill emissions, making ethanol, turn that into SAF. That production of that ethanol intermediate is commercial today and operating. We've produced, I'm not going to quantify, but we've produced millions of gallons of ethanol from steel mill emissions. Municipal waste is another example. Gasification of municipal waste can feed into our process and then produce ethanol, which goes into SAF. As we look farther out, CO2 coupled with the hydrogen produced from renewable energy is also a SAF feedstock, again, by production of ethanol and then transformation into SAF using the alcohol to jet pathway. So there's almost no limit to the feedstocks that can be applied to the SAF market using existing technology.
Thank you, Dr. Harman. With the time I got left, I want to just pivot to Dr. Hagg, and I have tremendous appreciation for what BIDO does and the pain of that valley of death that you have talked about, getting from lab scale to industrial scale. I wonder if you could speculate a little bit. Some of those projects get all through that, they get scaled up, all the bugs are ironed out, and they still aren't economic. I'm a market guy, and I also serve on the climate committee, and one of the things we keep coming back to on that committee is this International Monetary Fund report that says that the United States subsidizes the fossil fuel industry by $650 billion a year. I don't like picking winners and losers, but my goodness, if we keep subsidizing an industry that needs $60-50 billion a year to stay competitive, doesn't sound like we're picking the winners. Do you have some sense, Dr. Hegg, of how many of the technologies that come out that we deem to be economically uncompetitive, we only deem because the other technology is so heavily subsidized? How much would come forward if we took off those subsidies? Can you even guess at that?
That's a great question, and unfortunately, no. I mean, I simply don't have the data available to me to be able to speculate. But I think one of the other critical issues here is not only sort of the subsidizing that may occur, but also this issue of ensuring that technologies fit through the entire pipeline. And so not just solving one problem while forgetting how that solution integrates into the entire system. But related directly to your question, I'm sorry, I simply don't have those numbers available.
Maybe we can follow up offline. I'm out of my time. I will now recognize Mr. Weber for 5 minutes.
Thank you, sir. We had a hearing many years ago in 2017 that was focused specifically on biofuels. One of our witnesses was from the University of Michigan. So, Dr. Hegg, let's see if you agree or want to stoke up the rivalry with your institution. When talking about the billions of dollars spent on DOE's bioenergy research, development, and deployment efforts, he said, quote, "None of the promised cellulosic fuels have become commercially viable, even with subsidies amplified by mandates," end quote. As I mentioned in my opening statement, I think the Office of Science and the discoveries that originate there play a large role in the ultimate success of EERE. So, Dr. Hegg, Can you give us an updated opinion on DOE's bioenergy research efforts and how the Burr and the Office of Science can accelerate the overall development of biotechnologies? And as part of that update, no pressure here, as part of that update, could you provide an example or a success story from your days at Great Lakes Bioenergy Research Center or a project you were part of that started at the basic research level and is working towards being commercially viable? Dr. Hegg?
Sure. So I think one excellent example is when you think about designing dedicated bioenergy crops. And so at the basic research level, you can begin to design them for specific traits that make them specifically available, especially appropriate for bioenergy. In one classic example, researchers in the Great Lakes Bioenergy Research Center, not myself, worked out a system to make lignin, which is a structural component of the plant cell wall, degrade more easily. All right, so they were able to do that on the plant side. And then again, thinking about this idea of the pipeline, though, you have to think not just about the plants, but about the deconstruction. And so I was involved with the team sort of analyzing the impact of this new plant technology for how it might degrade more easily. And by performing this research, we're able to identify that in fact we could use lower chemical inputs to degrade the biomass into the structural components, specifically the sugars, so that they could be used downstream. And then, of course, again, thinking of this pipeline, having a group of people that can then take that the structural components that have been separated and turn them into biofuels and bioproducts. Overlaid on all this, and one of the challenges for a long time has been what to do with the lignin, again, this important structural component, which can be approximately 20% of the total biomass, but upwards of sometimes 40% of the energy content of the plant, and figuring out how you can turn that into useful fuels and or chemicals. And so I would say that a decade ago, the technology simply wasn't there to be able to effectively use that lignin. It was the old adage, the only thing good to do with lignin was to burn it. But we know that's not true, and we know that given the right sorts of scientific breakthroughs, we can in fact turn that lignin into useful fuels and chemicals. And in fact, we're working to do that across all of the centers. And we are in fact making great strides. So I think you'll see a big change once we stop throwing away an important component of that plant biomass.
All right, well, thank you. I appreciate that, Dr. Hegg. I'm going to move to Dr. Mayo now. Dr. Mayo, this committee is a big supporter of the national labs, including PNNL. We've heard a lot about the bioenergy research centers, but let's not forget there are so many different centers and projects and things going on at the national labs. The Environmental Molecular Science Laboratory, EMSL, the Joint Genome Institute, and Energy Frontier Research Centers all come to mind. So I want to give you a chance, Dr. Mayo, to talk about the end-to-end research collaboration. How does PNNL try to shape some of the activities that might not seem directly connected to bioenergy, especially those at EMSL, to assist the BRCs, or alternatively, how does PNNL work with the JGI and EFRCs to identify shared goals and mutually benefits? You got about 30 seconds. No pressure.
So an example would be the Joint Bioenergy Institute, JBay, which is a BRC. They've done some phenomenal work on driving synthetic biology, and this is directly fed into BITO, which is doing the Agile Biofoundry, looking at synthetic biology for specific targets. JBay has also had successes that have then gone on to the Advanced Biofuels, Bioproducts Process Development Unit, which is a pre-pilot process development unit. And so that has been a real stimulant in the Bay Area for new startup companies coming in with their ideas and ideas germinating at JBay and beginning to get them from microliters up to 100 liters.
I hate to cut you off, but I appreciate you're pretty knowledgeable about it. Thank you. I yield back.
Ms. Stevens, you are now recognized for 5 minutes.
Well, thank you, Mr. Acting Chair. What a treat to have you chair today's hearing. And as a Michigan native, of course, it is a real pleasure again to welcome Dr. Eric Hegg from Michigan State University. I'm wearing my green for you today, sir, as a witness for the committee for us here today. So, Dr. Hegg, you discussed the importance of advancing technology beyond the lab bench. Let's tease at that a little bit more. How does this work effectively within the Great Lakes Bioenergy Research Center? What have been your own experiences?
It's a great question. So at the Great Lakes Bioenergy Research Center, individual researchers work directly with their respective technologies office at their respective universities. And so once we have a nice technology at the lab scale that we think might be scaled up, we put out an invention disclosure. It is reviewed by the technology office, and if it's deemed to be interesting and important and promising, then it moves on to file a patent application, and hopefully, obviously, then ultimately a patent. Now, once we have a patent, it's important to note that all of the technologies offices within the various universities at the Great Lakes Bioenergy Center work together. The importance of that is that an industry can come in and they don't have to deal with multiple technology offices. They can work it with one center basically, and then pass the technologies that perhaps are developed at individual universities back and forth, or sometimes developed jointly between universities.
Yeah, and so let me try and get both these in here too, because obviously, we want to kind of talk about how critical it is that researchers from multiple fields tackle the R&D of the bioenergy enterprise. And so anything you can say on that would be important. And then tucked in that, I'd like to add that, Department of Energy has significantly grown its footprint in the area of artificial intelligence. And this committee, the Science Committee, has been highly supportive of that expansion. And for example, we led on the National Artificial Intelligence Initiative Act, which is enacted in late 2020, this is last term, to authorize the DOE to support efforts in artificial intelligence that cut across multiple missions. So anything that you could also speak to on the Bioenergy Research Centers as a platform for exploring how artificial intelligence can be used to advance DOE's goals in bioscience would be much appreciated. So I started with the macro question and then tucked in the micro one there too.
Okay, so getting to the first question, I think it's really critical to understand the interdisciplinary nature, of course, of bioenergy research, and I think all of the centers do a great job. I mentioned just some of the fields that have to come together within the Great Lakes Bioenergy Research Center. And in fact, at MSU, there's almost 30 different faculty involved in the Great Lakes Bioenergy Research Center, which together they constitute about 12 different departments in 5 different colleges. So it's really a huge group of people that is being brought together to ensure that you have this integrated process. Finding a solution in one area can in fact translate across the entire pipeline. So getting to your second question about the importance of computational work and especially artificial intelligence, it's outside my direct area of research by actually a long way. But I would echo what you said, which is the absolute importance of this type of research, really this type of capability in really any sort of a research project which deals with large and complex data sets, which in fact bioenergy research does. Being able to make sense out of this very complex, rich source of data, which comes from land management or genomics, or looking at product analysis, or looking at microbial pathways, is really invaluable. And taking all the data sets which are available throughout the literature and somehow combining them in a meaningful way is absolutely critical. But I can, if you're interested in more, I can sort of work with my colleagues.
Yeah, I mean, this is something we're going to continue to kind of tease out too on this committee, and we're obviously running on the short on my 5 minutes of time, but that was a really helpful start. And with that, Mr. Chair, I'll yield back.
The chair now recognizes the gentleman from Indiana, Dr. Baird, for 5 minutes.
Thank you, Mr. Chairman. I appreciate that, and I appreciate this subcommittee hearing on energy. And I have in my district one of the laboratories for renewable resource engineering, as well as a center for direct catalytic conversion of biomass to biofuels. And so it's an exciting time, in my opinion, to be looking for some of these alternative energy sources. And so, Dr. Hegg, you mentioned lignin. Would you care to elaborate on that a little bit? Because I think the forestry industries, which is a real carbon sink, the trees I'm talking about. And so I would really appreciate if you could elaborate just another moment on the lignin, if we can use that for a source of energy. What stage is that in, and how far along are we?
So I think exactly the state of it depends on sort of what direction you'd like to take it. So one direction that you can take the lignin, which again is this complex biopolymer that's an important structural component of the plant cell wall, and you can sort of extract it, and you can use it, I'll say, more or less directly as a polyol replacement. In other words, it's got a lot of alcohols on it, which can make it useful in certain applications, such as various types of polyurethanes. And so that is a market which actually already has a lot of industrial interest. And in fact, one of my colleagues in the forestry department here at Michigan State University, Mojgan Najad, collaborates quite a bit with a number of industries all over the nation. And so that is, I would call it a mature technology, but it is already sort of on that road to being able to make an important contribution to the overall bioeconomy. Now, another thing that you can do with that lignin is depolymerize it into its constituent monomers, and then use those monomers either as a fuel directly or to be built up into other types of useful bioproducts. That technology is coming along. It is still much more nascent. It's challenging. It's challenging to break apart lignin into monomers and to keep those, and to then separate those monomers and stop them from reacting with each other in a sort of uncontrolled way. And so that's the challenge. Chemists are learning to do that, and they've made great strides over the last, I would say 5 years. There's a long way to go, but they are really making great progress. So I think that's, I think that will get to the same technology level in the next 5 to 10 years. At least I'm hopeful that it will.
Super. I'm glad to hear that. So would you have any further comments about the Centers for Direct Catalytic Conversion of Biomass, just to give you the opportunity to make a comment about those centers, those C3 bios?
Yeah, unfortunately, I don't have enough of experience with them to be able to speak with any degree of authority.
Okay. Dr. Leaky, you have any comments on either one of the questions that I asked?
So the CABI research portfolio focuses heavily on a complementary approach to the work that Dr. Hegg described on lignin. And so we focus largely on producing oils within the plant that can be easily extracted as a drop-in biofuel that increases the value of the biomass per acre. So that would complement the approaches that he described.
Well, the advances we've made in biotechnology in recent decades are tremendous, and it really enhances our ability to provide food and fiber and mitigate some of this climate change. So anyone else have a comment? If not, I thank you and I yield back, Chairman.
We are going to continue with the PhD caucus, and Dr. McNerney from California is now recognized for 5 minutes.
Well, I thank the chairman for that recognition and the hearing, and I thank the witnesses. This is really interesting and important, and I'm glad to be a part of it. Dr. Leaky, you discussed how artificial intelligence can be used to increase efficiencies in the traditionally laborious RD&D processes. So I'm going to follow up on Ms. Stevens' question. How is AI beneficial to bioenergy research and development, and how can the government support further use of this technology?
Sure, thank you very much. Yes, so scientists within CABI are using machine learning to help address a very broad range of questions and accelerate our research progress. To give you some flavor for it, this includes designing new enzymes and metabolic pathways, automating normally laborious and inefficient steps in genome editing, as well as automatically analyzing images from microscopes, drones, and satellites to much more rapidly identify which crops and locations bioenergy would perform best for bioenergy production. I will say that this is a good example of there being some valuable interactions with federal funding agencies beyond DOE. So the University of Illinois, for instance, leads 2 artificial intelligence research institutes, one funded by USDA, one funded by the National Science Foundation. And I'm pleased to say that even though those are just over a year old, we have got significant overlap in scientists between those projects and CABI, and real valuable relationships building there. And we have some examples of AI accelerating progress, particularly on our microbial platforms, by up to an order of magnitude. So I think it's a really ripe area for more work.
It's not only a research tool, but it's a collaboration tool. So I'm glad to hear that.
Yes.
Dr. Mayo, the climate benefits of bioenergy are still widely debated, with different conclusions about the carbon intensity of biomass feedstocks. Do you think there are gaps in the life cycle assessments of biomass feedstocks?
The life cycle assessment modeling is still an evolving field. I'll give you an example, particularly where products are perhaps used multiple times. We have not seen that really come to the fore. And there's a real opportunity to actually be more transparent and have discussions about what are the assumptions in anyone's models, the boundary conditions in the models, and how it leads to a certain conclusion. And it's okay to have discourse. That stimulates overall for the entire community of life cycle assessment modeling and land use change modeling to actually move forward.
Well, what barriers are remaining for conducting the kind of research or for creating partnerships for commercial development projects?
Barriers for commercial, with regard to the life cycle assessment, or with regard or just to commercialization in general?
Well, let's talk about the life cycle assessments.
With regard to life cycle assessments, looking at it more holistically, that is not just about greenhouse gas emissions, it's a myriad of other metrics of sustainability or sustainability indicators, such as water, the quality of the soil and how that is treated, just to give you 2 examples. And so it is a multifaceted challenge, and you are doing trade-offs across these numerous facets or success metrics. And so having a program where you can put forth in a transparent manner how you assessed what your crop did in the field and the water usage and the energy usage in your process, and engage people like the Roundtable for Sustainable Biomaterials is an excellent way to go forward.
Okay, thank you. I believe I'm about out of time, so I'm going to yield back to the chair.
I'm looking for Mr. Meyer, and I don't see him, so the chair will now recognize Mr. Obernolte from California.
Thank you very much, Mr. Chairman, and thank you to the witnesses for a very fascinating hearing. I'd like to ask a couple questions about the need to increase feedstock supplies, because that's been a kind of a recurrent theme in our hearing today. And as a representative from California, as I know the chairman is, it's no surprise that we've had a couple of worst years of wildfires in the entire state's history. And one of the things that's been discovered is that our traditional approach to forest management is insufficient, and we're going to have to pay a lot further attention to things like fuels reduction in the future if we hope to tame this activity. So, you know, I'm interested in the fact that when we do fuels reduction in the forests, we come up with a lot of biomass, but we really don't have anything to do with them. You know, we try and create energy from them, but that creates a lot of soot. It's very inefficient. That process requires government controls. I'm wondering if that can't have, that biomass supply can't have a role to play in maybe the production of aviation fuel through the processes that we've been talking about. So let me start with Dr. Mayo, since you'd mentioned you know, the need for expansion of the feedstock supply. Is there some kind of process that this forest-based fuels reduction biomass can be used for that purpose?
There is, and particularly if you look at managed forests, and a key aspect though is you always have to bear in mind the accessibility to that particular resource. So if you're doing thinning or putting in fire corridors, getting that resource from that site has traditionally been, or if you have logging roads, that's fine. If you don't, it's a challenge. And so that has pushed the research on, can we have systems that are modular and can be distributed to those locations to make an intermediate that can then subsequently be taken from there that doesn't create the soot that you mentioned.
Right. Yeah, I mean, obviously that's going to be a recurrent theme, no matter what use you put that biomass to. But, you know, given the fact that that's a problem we have to solve anyway, I'm kind of optimistic that maybe, you know, a pathway can be found there. And Dr. Leaky, you also brought this up in your testimony. Do you think that the use of this forest-based biomass might be a kind of a substitute for actual food stock crops?
So the work within CABI focuses specifically on the use of grasses as our feedstock. And so I can't testify directly to the use of woody feedstocks.
Okay, Dr. Mayo, going back to you, you were talking about how difficult it is to create an industrial process to make a feedstock-based fuel that allows for variability in the feedstock. And obviously, if we're talking, you know, with fuels that have been reduced from forests, there's a lot of variability there. What do you think we can do to overcome that particular problem?
I think what we can do is recognize the issue that there is clearly, if you think about Gaussian distributions, pick any parameter of a feedstock like particle size, there is a particle size distribution, and it's not good enough just to sit on top of the mean particle size. It shows you your technical feasibility of the process, but really you want to go out, perhaps if you want to be 95% sure you can deal with all the variability in that wood, you go out 2 sigma either side of that mean to look at the tails of that distribution where the quality varies greatly, and show that your process is both resilient and robust. And then that will allow your process to transition to industry with a greater certainty.
Right. Okay, well, thank you. You know, I'm really happy that we're having this discussion, because we have a big problem with fuels reduction in the Western United States, and what to do with that biomass. Because if we can burn it, which will just desequester the carbon that's stored in it. We can let it decompose, but that over a slower or longer amount of time also desequesters the carbon. Or we can figure out some way of making productive use of that carbon that results in avoided carbon through other channels. And I think that turning that into a feedstock for an organic-based fuel is a really good solution. So I'd love to see more attention paid to that. I'd love to see some more research, and I'm very happy that this committee is taking a leadership role in that. Mr. Chair, I yield back.
Thank you. And not seeing Mr. Lamb, the gentle lady from North Carolina, Ms. Ross, is now recognized for 5 minutes. Oh, and before I introduce her, I apologized for not recognizing the other member of our PhD caucus, Dr. Obernolte. So apologies for the misnomer. Ms. Ross, you're now recognized.
Thank you, Mr. Chairman, and I'm a member of the lawyer caucus. And I want to thank the Chairman Bowman for holding this meeting. And as a member of the Lawyer Caucus, I represented several different bioenergy clients in North Carolina, including those who used wood waste, those who turned hog poop into power, and I also represented people who dealt with municipal waste and turned that into energy. And I'm very interested to hear the insights from our panelists and the status and the pace of DOE bioenergy research, and obviously more research and development coupled with environmental justice and economic considerations are needed to ensure that we can maximize the use of bioenergy to our benefit. And as I said, I did represent a client that dealt with wood waste, and wood waste has been both a positive and a controversial issue in North Carolina. And the production, particularly of wood pellets, has created some environmental justice concerns that need to be considered as we move forward. Specifically, some of the wood pellet plants in North Carolina and across the United States are located in rural and low income and predominantly minority areas. And the plants can produce fine particle pollution, carbon monoxide, and can degrade the local air quality. These effects disproportionately harm minority and disadvantaged communities given their proximity to the plants, putting them at higher risk of suffering from health consequences. And so to all of our panelists, are there best practices that can prevent environmental injustices such as these? And are there immediate steps we can take to reduce the increased health risks associated with these plants? Anybody?
You should be able to readily address the particulate matter if you have any particulate matter coming off. And there are regulations on volatile organic compounds coming off from the production of, say, a roasting, like in torrefaction or in the production of pellets, that those volatile organic compounds should be combusted prior to going up a stack. And the EPA has guidelines on both to help all communities.
Okay. Does anybody else have anything to add? I have a second question. Also, the selling or moving of bioenergy in existing pipelines. So I'm talking about what is referred to as renewable natural gas. Requires negotiation with pipeline owners, and this requires coordination and careful attention to the movement of other gases in order to avoid dangers and combustion. And the North Carolina Utilities Commission is dealing with this right now and has several pilot programs for bioenergy moving through natural gas pipelines. Dr. Harman, how do we ensure that the Pipeline and Hazardous Materials Safety Administration, PHMSA's regulation of these transactions balance the safety risks without being over restrictive on something that can be a positive industry?
So first, I have to acknowledge I have no expertise in natural gas pipelines or the complexity that you described. What I would say is that if we think about renewable natural gas as something that can be used closer to its source in conversion facilities that make, for example, sustainable aviation fuel or make chemicals from that resource, in that way, we would obviate the need for some of the complexity that you described.
Yes. Yeah, that is a great point. And actually, those projects are moving forward much more seamlessly. Interestingly, in North Carolina, our utilities get credits for using renewable natural gas. And so that's raised this issue with the pipelines. But hopefully we can submit some other questions and get answers to those. Thank you so much, Mr. Chair, and I yield back.
It appears that we have no more Republicans on the panel, so we will now turn to Dr. Foster from Illinois for 5 minutes. To our distinguished panel, we've got you tied. We've got 4 doctors to your doctors. We'll see if you raise this on the next round. Dr. Foster, you're recognized.
Yeah. Well, I think that probably the thing that trumps this is the PhD from the University of Wisconsin that Dr. Hegg has. And so as a graduate of Wisconsin myself, I think that we can all acknowledge that probably trumps everything. But there is one of the big knocks against biofuels in the early days had to do with the fact that it was unclear that things like corn ethanol were even carbon neutral. And there are some there at the time were very large fossil fuel inputs to making well, corn ethanol, for example. And so the 2 big things that have been talked about to eliminate those are the ability to eliminate ammonia fertilizer. And there are various biological approaches to that. I think Pivot Bio and some other companies are actually, so I was wondering if you could sort of give a quick status report on that. The other thing that seemed promising is there's a company called Clearflame, I think, that apparently has cracked the code on how to make diesel engines work with full thermodynamic efficiency and very low soot emissions using, for example, corn ethanol, methanol, or a variety of other stocks. Apparently that required some bright new ideas from a startup that's just gotten a lot of follow-on funding. They're driving trucks around with corn ethanol at full thermodynamic efficiency. And so I was wondering what you think the promising ways are, how far along are we, and what are the promising road ahead for further reducing the carbon footprint used to produce biofuels? Dr. Mel, do you want to have a shot at that?
Yes, thank you for bringing up that topic. There has been a lot of progress in introducing sustainable practices or best land management practices and utilization of lignin and other practices, and going towards extracting corn oils and extracting fiber that have increased the greenhouse gas reductions. You've seen the march from a 20% reduction initially for corn ethanol to, when you have other processes on the site, going to around 45%. You're right about there are different ways of utilizing organic fertilizer. There's a terrific opportunity that DOE and USDA are looking at, and there's a lot of science that is needed to look at the interaction of fertilizer, the soil bacteria communities, the root system of plants, and the interaction between those and the species and the transport, and keeping it on the field. Farmers pay for their fertilizer. They do not want it leaving the field. And so there are opportunities where you can use energy crops or perennials with a deeper root system, to perhaps on the drainage from your field or the edge of your field, so that you keep your fertilizer in the field while preventing your fertilizer from going into streams that can then go downstream and affect organisms like microalgae to give you a harmful algal bloom.
Yeah, Dr. Leaky, did you have any comments on?
Yes, I could certainly contribute to that conversation. So within CABI, reducing the greenhouse gas emissions in the form of nitrous oxide and maximizing the efficiency with which plants use nitrogen in the soil is of strong interest. As with a number of other aspects of this problem, I think it's best addressed with next generation bioenergy feedstocks. And our team is working on that in a variety of ways. Actually, having feedstocks which are perennial themselves is exceedingly valuable because they recycle the nutrients from one year to the next. Similar to what Dr. Mel just mentioned, our team is also really actively working on understanding how microbial partners in the soil, and in some cases, the chemicals released from the roots of these crops influence that cycling of nitrogen, and how we can manage them optimally to retain most of that nitrogen in the plant. And then last but not least, we can actually engineer the plants themselves to try to use the nitrogen more efficiently. So there's a number of strands of research on that topic.
Now, do you anticipate that within a small number of decades, we'll be able to essentially eliminate the need for ammonia-based fertilizer? Is that a realistic hope?
I think we can really realistically hope to substantially reduce its use. Whether we get to a total elimination or not is harder to say.
All right, thank you. My time is up and yield back.
Thank you to all of our witnesses. Before I bring the hearing to a close, well, I'd like to thank all of our witnesses for testifying today. I have a statement for the record from the Biotechnology Innovation Organization, which I would move to be incorporated into the record. So ordered. The record will remain open for 2 weeks for additional statements from the members and for any additional questions that the committee may ask of the witnesses. The witnesses are excused and the hearing is now adjourned.